Okay, so in this video, we're going to take a look at binary options and some numerical techniques that we can use to estimate the value of a cache or knotting binary option. We're going to adjust, so we will compare the estimation accuracy relative to Reimer and Rubinstein, which if Black-Scholes assumptions stand up, then Cox, Ross, and Rubinstein should converge to Reimer and Rubinstein 1991. And we will also take a Leisen Reimer version, same tree, same design, but we will take a Leisen Reimer model and adopt it for binary options and compare it to performance. Now, in advance, just to note, there are two functions here. One based on code from Carryback, which was just basically a European call option. And we just make some adjustments so that it changes to estimate the value of a binary, cache or knotting. We likewise use Cox, Ross, Rubinstein code based on VBA provided by Espen Hogue. We make some tweaks and likewise estimate Cox, Ross, Rubinstein using the Cox, Ross, Rubinstein approach, estimate the value of the cache or knotting, and it will also output some option Greeks. And then finally, the Leisen Reimer model is based on Espen Hogue code from his textbook, A Complete Guide to Derivatives, and we'll leave a link to that in the Vinegar Hill here at some point, so that you can track back. But we make a small change in the code, and we then estimate the cache or knotting binary option using a binomial framework. Okay, so let's just copy the code. And we'll start by just copy the Cox, Ross, Rubinstein code, both from Carryback and Espen Hogue. So we'll copy, and then I'll go into a spreadsheet that we've already set up, in which we had estimated a cache or knotting. So let's have a look here for a moment. Binary, full spread, cache or knotting. Okay, so we'll compare with this model here. We need to input in the code. Okay, so we'll insert, and maybe I'll give these names. So the first segment of code here was just basically Black-Scholes. BS, I would say call. The second module here was, let's double click, binary. So cache or knotting, cache or knotting, right? So we'll change the names here. And this was based on Rubinstein, Reimer and Rubinstein, right? 1991. And then we'll insert a new module, and we'll say cache or knotting, cache or knotting. And this time it's for binomial, right? Using binomial. There's two binomial frameworks we'll use: Cox, Ross, Rubinstein, Leisen, Reimer. The first couple here are for Cox, Ross, and Rubinstein. So it looks as if we have a small issue. Let's see if we can resolve. First segment of code looks fine. Second segment of code, perhaps we'll remove public. See if that resolves that. Probably the problem here is we just need to put it on the following line. Okay, so that seems to resolve that. And again, likewise here, going to the next line here just means we should put on the line immediately below, and that looks fine. Okay, so those functions are there. We can format later on to tidy them up. So let's just for sake of argument, let's go back to the cash or nothing. And this was a function that we had used previously. And we'll just paste, home, paste. We might just increase the size here a little bit so that we can amplify and get a clearer look. And so the first estimate here is Black-Scholes, BS. So if we have 100 is the stock price, and the exercise price is 100, and the risk-free rate is 5%, dividend 0, time period 1 year, volatility 20%. Then the value of the call option, Black-Scholes call, is 2045. If we, for a binary option, cash or nothing, right, using Reimer and Rubinstein model, then we would have here, let's just explore this, cash or nothing call, 106. So let's change the cash here to 100 to denote how much you win in the event of the option being in the money. Okay, so to see the payoff here on this, the cash or nothing would have a payoff framework, something like this. So you would win, let's change to 100. Right, and let's, right, so we change to 100, and what we observe is that in the event of, and we must have here 100 as well, so equal to what we have here, perhaps would be better, and then change this to 100. Okay, so in the event that the option is in the money, we get a payoff of 100, but the cost of setting up the option was 50, with a volatility of 20%, was the cost of setting up the option was 53. So we gain, in the event that the option is in the money, yes, we gain 100, but after absorbing the cost of the premium estimated by Reimer and Rubinstein, we would clear 46.76. So the cost of the strategy is 53. We would win 100. 100 minus that 53 yields us this 46. Okay, so that's the payoff here in red, right? Okay, so that's where the 53 is coming from. Let's say we try the same again, but this time we're going to use the cash or nothing. So let's check the name of the functions. What's the functions? We have European call cash, okay, and that's from Carryback. Okay, so just put in European call binomial cash, right? And we can come up to FX, and we can map in the values, 100 for the exercise, 5% for the risk-free rate. The volatility is 20%. The dividend was 0. The maturity was 1 year, but binary options all very often have maturities less than 1 year. We'll go initially with 100 steps, and the cash is equal to, okay, let's say 1,000 steps, and the cash amount is equal to 100. Okay, and we get 52, which is not quite it's not quite the same. It's a bit different. So we could say equal to here and pull down, right? And they're out of sync, it would appear. So that's the Carryback code, European call binomial cash. If I use Espen-Haug's code, it's CRR binomial B. Okay, so let's try that. Right, so again, we put in equal to CRR binomial B, FX, and then we're prompted the cash amount. Again, the ordering here is a little bit different. Makes no matter. Is it a call or put? It's a call. S is equal to 100. K, the exercise is 100. The time period, maturity is 100. The risk rate is equal to 5%. B is the cost of carry, so it's actually R negative K. So I can say R negative Q, R negative the dividend yield. So B is the cost of carry, and it's equal to R negative Q. V is the volatility of 20%. N is equal to, we're using 100. Okay, and again with with this framework, we also get delta, gamma, and I think it's theta. We'll look at that in a moment. 56 now. Why the difference? Because this was done. If we go back to this function, cancel. If we take this function and go fx for n, did we declare n is equal to 1000? So we'll change that to 100. And we get 5696. So obviously, if in a 100-step tree, we get values. Okay, first of all, the carryback code is yielding the same result as the Espen-Haug style code. If we increase the number of steps, so again, go fx equal to the number of steps here, we'll make it 1000. That'll bring us closer to, so we're getting convergence to the 53. We'll do the same here. We have to go fx and see where we put in code for n. So we put this equal to 1000. Okay, and you can see we're replicating the 52045, so that's fine. This is delta, this is gamma, and theta. So if we look at Espen-Haug's code here, not only do we get the Cox-Ross-Rubinstein, but we also get the delta, the gamma, the theta, right? Okay, so that's great. But not terribly accurate relative to the true value, which is given by Reimer and Rubinstein. Now, when we use so both of these are Cox-Ross-Rubinstein, CRR, and we use Rubinstein, Reimer and Rubinstein, and the last one we use a Leisen Reimer. And this is true. And we'll take the same numbers again. We run the code. This time, again, we better check the name of the function. Go back into the developer tab. And we'll check Leisen Reimer for a moment here. Actually, we need to use green. Go back to the Leisen Reimer function. Okay, so let's note the name of the function Leisen Reimer binomial. Okay, that's fine. Let's copy. And then we go back into Excel. And then we look at go into the developer tab. So we have Cashew-Knotting binomial. Let's just come down here below Espen-Haug's code for Cox-Ross-Rubinstein, adopted for binary, okay, which we've done here. That looks okay. We've an issue here. Okay, let's just sort that out. It looks fine. And let's go back into our spreadsheet. So Leisen Reimer, binomial B denoting binary. And we can invoke the parameters cache amount 100 is Is it a call or a put? It's a call. 100 for the stock price, 100 for the exercise price. T is equal to 1 year, and risk-free rate 5%, same as before. V is the cost of carry, so it is R negative, Q the dividend yield, and V is volatility. Right? Have I got everything? One last, how many steps? I think we're using 1,000. So 1,000, an extra 0. Let's run. And this time we get a value here that's more consistent with the true value. So Leisen Reimer seems actually quite good. Now we can stress test this a little bit. Let's change this to 90 for the stock price. Compare the other two. And we have 33.59, which here is replicated here using Leisen Reimer. Very good. Less Cox Rubinstein performs less well here. Okay, let's go with 110. And again, if we look here at Reimer and Rubinstein, 1991, the value we get here is consistent with the value using the Leisen-Reimer binomial framework. Cox-Ross-Rubinstein, less compelling. Just the accuracy is just a little bit out, not hugely out, but sufficiently out. The good thing about Leisen-Reimer, we get values here for delta, gamma, and it's not theta. We can't get the value for theta here. So the first two are fine. We get the value for delta and gamma. This last one is the same value. I think it's not a Greek, right? It's not a Greek. Okay, so in terms of performance here, Leisen-Reimer looks to be the best numerical technique, or at least better than Cox-Ross-Rubinstein when trying to replicate or develop a model that converges quickly to Reimer and Rubinstein.